Okay, we have quite a few people here. We're missing a lot too still. And let me tell you the okay, so that everybody is on board, okay? My computer is having problems with the charge. It's gonna work probably for an hour or maybe less. So what I'm gonna do is we're gonna take a break for about 5 minutes or something. Hopefully I'll readjust the power adapter on it and it's gonna work. But I need to take a break anyway because we're going to have two labs today. We're going to have 11 and 12. This is the last session. There will be no more lab session with you guys as far as labs is concerned. And that's 11 and 12 are going to be, one of them is going to be basically for extra credit. Which one is going to be extra credit is going to be you to decide that. So if you can, you say, okay, I'm going to lab 11, and that's going to be graded, and that's the end of it. There is no problem, no harm done. If you do a lab 12, same thing. You're going to get that graded. There is no harm, nothing done. If you decide to do both of them, you're going to tell me specifically which one is going to be for extra credit, because it's going to be graded out of 10, not out of 20. It's half the credit for the normal labs, okay? So I need to know when you're submitting them that this is for extra credit, and the one that you leave without a mark, that's going to be the regular lab. Is everybody understanding how this works, at least for the last two labs? Okay, very good. So now you have two labs. One of them is probably more work than the other, so you're going to make that call yourself. And but do ask, okay? Don't leave the questions to the last day, and when the labs are due, and then you start thinking about it, and then you will be confronted with some problems. Now for lab 10, and I know ask the question, is it here? No. Okay. For lab 10, question 7, I was hesitant on it last time when we did it, and the question was basically kind of, I left it kind of ambiguous because I was not sure honestly how I'm going to grade that if I were to grade question 7 at all. So I decided it should be the answer to, okay, the last question basically who asked. Anyway, oh man, the question 7, because I was hesitant on it last time basically. So what I thought we were going to do for question 7 is the following. Answer it, if you decide to choose the answer it, you're going to get it as an extra credit. That's basically how I'm going to do that, because quantum waves is something that is a little bit hard to understand, although there were 2 videos plus a Geogebra activity for it, but you're not really the point I was trying to make in here is that question 7 is optional. If you decide to answer it, maybe for extra credit. If not, ignore that question, okay? So am I clear also on lab 10? Yes? For question 7, that is. I need feedback from you guys. Okay, very good. So let's get into the labs quickly, because we are pressed on time because of the situation that we're in. And assignments. We're going to go straight to lab 11. Lab 11 looks kind of a little bit easier, but don't be fooled with the content, okay? With the at least the amount of things that are displayed in there. So I basically, okay, why did I do the second one? I just wanted just the instructions in here. Okay, so let me get the Zoom again. Okay, I will ask one of you guys, or at least 2 of you, to please make a note of anything that happened, like the one that happened with this user who I did not recognize. I asked her several times. So if you guys suspect somebody is doing something funny or not part of the class, please let me know immediately. Okay, I want them to be removed and not to stay with us, linger any longer. Okay. So anyway, let me go to sharing the PDF file. So this is basically, did you guys do atomic structure? Yes or no? Oh, you did not do that, the atom? Okay, Okay, basically, the bottom line is the atom is made up, of course, of a nucleus, and it has the. Okay. Anyway, and it has an atomic cloud, and the electron cloud. The electrons can sit in certain energy levels. Okay, there is only discrete level of them that they can sit with in them. So if you think about it, is that okay? An electron can be here or here in terms of energy. Okay, not in terms of physical location. Okay, so it can have this much energy or this much energy or this much energy, depending on the atom. Depends, of course. That's the only thing that is going to determine that. So here is the nucleus. Okay, or let's present it, not the nucleus. Let's represent the energy levels of electrons. So an electron for a given atom can be in this energy level, or can be in this energy level, or can be in this energy level, or can be there, depending. Okay. Now, if it's excited, if it's supposed to be here and now it's moved in here, the electron absorbs energy to do that. So this is what is called an absorption spectrum. You send energy to the light to an atom, and the electron will take it depending on the wavelength of the light. If the wavelength of the light is too short, namely the frequency is too high, there is a lot of energy with that, so it could end up here or here. Actually, it could take that much energy and get excited so high. This is called an absorption spectrum, because you shine a light on a certain material, and then when you look at it at the end, you will see some frequencies are missing. So what happened to them? They were absorbed by the material. So when you analyze the spectrum, you will see what are the missing frequencies. There is one here, there is one here, there is one here that is missing. You call that an absorption spectrum. Now, you can do it the other way around, basically, because when the electron is excited, when it moves out of its normal state, basically, it wants to go back to its ground state. So, for example, if you warm it up, if you heat the atom, the material, the atoms will be excited. They will move out of their ground state, where they're supposed to be. And those electrons need to return back to where they started from. In doing so, they will emit light. So they will emit frequency. So, for example, there is a potential that one that was living in here come down from the second level to the ground state, or the one, for example, from the third level to down to the ground state. So it doesn't matter where the ground state is. It doesn't matter where the excited state is. If it has an energy in it, it's outside of its own level where it needs to be, it will give off energy for it. So basically, you're analyzing light from a source, for example, that is excited, and all of a sudden you see a bunch of frequencies. You run them through a system, or you look at them if they're in the visible region, and you see, oh, there is this frequency, there is this color, there is this color, there is this color, there is this color. So this is called actually an emission spectrum. You see the difference between them? Emission is coming from the material itself because it was excited. And absorption, actually excite the element by sending light through it, and the frequencies are absorbed. And in this case, you analyze the frequencies, and you will see that there are some that are missing. So that's basically the difference between them. Now, if you shine light and it doesn't encounter material, and the entire spectrum is going through, we call that continuous spectrum. So that's the difference between the three. So there is a continuous spectrum that is unchanged frequencies. Basically, all the light are in there. They leave, they come back, you analyze them, nothing is missing, nothing is added. Now, an emission spectrum is added. So you look at the spectrum, everything is dark, except that there are some lines that are appearing in there. And those are coming from someplace, okay? Now, an absorption spectrum is missing lights. Basically, you have a bunch of light, the entire color is there, the white light is there, and there are some lines that are actually clearly missing from the spectrum. Where did those go? They were absorbed by the material that was between the source and the analyzer. So that's basically how you analyzer can be your eyes, but it doesn't matter which the analyzer is. Now, there is a problem here in a sense. Oh man, I lost my train of thought quickly in here. Now, the idea is the following, and that's a very important point in here. Every element on the periodic table has its own unique signature. if I see a certain sequence of frequencies present or in the same time missing, if I see them present, first of all, I say that element is the one that that sent me those frequencies, and it's only that one, not two. Okay. Now the same thing. If I see frequencies that are missing, I can tell you that that element is present in the sample that you're analyzing, because that's the only one that can do that, that can absorb all of those ones. So that's the power of spectroscopy, because it can be used to distinguish the presence or the lack of specific materials. So you're going to take, do a spectral analysis, look at the frequencies and say, this line and this line and this line, this line are the signatures of hydrogen. This line, this line, this line, and this line, and this line, and that line, and this line, and there are probably more dozen lines. They're actually for argon, and this one, for example, is for helium. At least a bunch of them. One of them is not good enough, so we have a bunch of them, and the frequencies are specific because this distance, the gap in the energy between different levels, is really specific to the material itself. Do we have a rough idea of how spectroscopy works now? Of course, if you watch a lot of shows on TV, the ones that deal with criminals and all of that, and trying to analyze what called the cause of death of so and so, they use spectroscopy to analyze the composition of whatever they're trying to analyze, and also it's used for example, for studying faraway object. Nobody went to the sun actually and get a sample from the sun's basically surface. Let's say the sun has hydrogen and helium in its surface with this abundance. We had to do spectral analysis. Nobody went to the sun, let alone to the nearest stars or any stars that is. And we do all the time spectral analysis for the stars, and we can determine their composition, not leaving our laboratories. And the same thing, and it can be used for all kinds of things. Spectral analysis is a very powerful technique, and it all relies on the idea that the energy levels are discrete and they are unique for specific elements. Does this give you a rough idea of what this is? Of course, if you read more about it, hopefully it's going to clarify the idea better. Yes? No? Okay. Yeah, I know it's kind of too much to take, especially if you have never seen this stuff before. It's probably going to be a lot. But I'm hoping that somehow you will be able to proceed with the lab. So basically, this is what I was talking about. So this is an absorption spectrum. It takes energy and moves from one energy to the next. Okay. Now in this schematic, it shows the gap between the energy levels is the same. Basically, is the same gap. This is not true. Usually, the gap is between one level and the next is not the same. So that's not true. I mean, it's just a representation, of course. Now the emission spectrum is when you have an excited electron, it has to give off that energy and go back to the ground state to where it came from, and in doing so, it's going to give us light. So the frequency of this, at least particular example, the gap between this level and this level is the same gap of this level and this level, and that is basically the same color. So if you said red, for example, in here, it's going to come out red on the other side too. So this is but if it comes out, for example, from this level down to the ground state, this of course will be a higher frequency. So this will be probably shifted toward the yellow or something. If this were actually red, this one will be actually probably green or something. This one, probably the one that is here and there, it's a smaller gap, so probably it's going to be maybe infrared. We cannot even see that. Okay. So, but we're talking about the visible spectroscopy here. So everything that we're talking about ranges in the visible range. Okay. So anything that is infrared or ultraviolet, we're going to consider it for this. Because the way we're supposed to do it in the lab is actually you go and you actually look at it with your own eyes, and your own eyes can detect only the visible light. Okay, anything high frequency or low frequency, it's not going to be able to read it. Here is the apparatus in the lab. Basically, what you have in here a very highly energetic, excited gas inside the chamber, inside the lamp, that you run a voltage across it, and the voltage basically will excite it, will make it so that it's super excited, and it's going to give off light. It's going to have an emission spectrum in this case, because it's going to give us light. And the light is going to come off from here and is to travel this distance L. This is the distance L in your graph, in your instruction. So this is L. And when you look at it in here, when you are looking at here, that's why you have to have 2 people for the lab actually to do it. And when you look at it in here, when you look at it from this angle, it appears that there is a big white light in the middle, okay, or whatever color that is, okay. So if they shift it toward the red, it looks like it's a reddish color because there are a lot of probably frequencies dominated by red next to one another. So the central one will always look the same. We try to put there is a meter second here, and we try to put this one right around 50 centimeters. Okay, right around that point, 50 centimeters. So what you're doing here, but when you tilt your head a little bit to this side, it appears that there are some frequencies in here. There is probably a blue, there is maybe a green, maybe there is a yellow. Oops, next to them. There is a yellow here, and maybe even there is a red in here, okay? That's what you see. But if you look at the other side, you will see the same picture backward. So there is again the blue, there is probably the, what is it, the green I called it, there is actually the yellow, and there is the red. Not necessarily centered in the way that I did it in here, okay? But at least you have an idea in there. That's basically where the locations are. You guys see the point in here? The same lines are going to be repeated one or the way or the other. Now, what is going on with the diffraction grading? Diffraction grading is actually, I have one in here. Okay, it's made up of very, very small lines in here. It has a lot of lines. It has, this one has 500 lines for every millimeter. So if you take a millimeter, how big is the millimeter in here? Okay, I'm trying to think. Yeah, it's this, basically this much, okay? The gap. There are 500 lines, okay? So that's the distance between each and every one of those lines in 1/500 millimeters, 0.002 millimeters, or 20 microns, okay? Or actually 2 microns, 2, because 0.005. So it's 0.002, I'm sorry, 1/500. So it's very, very, very small. So it's about 2 micrometers. It's extremely small, the gap between each 2 lines, because you have this much and you have 500 lines in them. So when light comes in there, it's going to be diffracted. It's going to be broken, at least for you. So when it hits you in the eye, it appears as if it's coming from here. It's coming from here. You guys understand that? But when it comes in here, it's going to be broken. It's going to be diffracted from what we saw in the previous lab. So it's going to be diffracted. When you look at it in your eye, it appears as if it's there. It's like, for example, the lab before, when you are, for example, standing on top of the pond, and you see a fish in front of you and under the water, so you grab it, you push your hand trying to go straight to grab it, but you miss it. You're always going to miss it because it appears to be in that location, but actually it's in a different location. That's because of the diffraction. You guys understand? So because light, let me try to draw it in here. Here is the surface between the 2 regions. So light is coming in here, hits the surface and diffracted. Oops. Okay, it's disappeared in there. So for you, the fish looks like it's here. Okay, you say, I swear the fish is there. So you go straight out trying to get it, but the fish actually is in here because the image that forms in your eye in here is coming in here, refracting through this, and basically giving you the impression that this is where the location of the fish is. You guys understand the idea? This is the same thing. This is exactly the same idea. Light is coming from the lamp, hitting the diffraction grating. You're looking at it in here, and you can tell it's in here. But your friend who's standing near to the meter stick can't see anything because he's actually on the other side of the diffraction grating. So you're going to tell him, hey, move closer. I can see red there. It's there. It's next to the 20 centimeters or whatever you're looking at it. Or not. If this is the 0, probably next to the 70 centimeters or something marking. Make a mark of it there. So he's going to make a mark there. And then tell him, okay, move to the next one. I see actually different color now, green, and so on and so forth. Obviously, this is the light diffracting through the diffraction grating. Now you tell them in the same time, please, can you go to the other side and look at it? Here is the blue. It's around 30 centimeters. Here is the green, is probably around 27 centimeters, and so on and so forth. And now you have a data. This we're going to call it x1, the closer to the 0. So this will be my x1 on the table, and this will be the x2 on the table. Okay? For the same light, for the same color, because it's going to be replicated one side or the other of the central location. So at this point, you have, okay, I have x1 and I have x2. Those are the data I'm collecting. I'm going to go and put it on my table, basically. Okay, here is the spectrum I was talking about in here. Here is a visible spectrum for both helium and neon. We don't need neon for our lab, but just to give you an idea, this is all of these lines is just neon. So if you want to make sure you have neon in your sample, you're going to look all of these lines from this faint blue to this green to this greenish between, and this is yellow, and then it starts orangey and then red and then a little bit faint red, and actually there is another line in here and there is a line in between them. So all of this, whether it's bright or dim, is a signature of neon. Same thing in here for helium. You have this one, there is another one actually in here, there is another one in here, there is this one, but these are the ones that we're referring to. This is the 706.5 light. So this is the 706 spectrum for, the red is longer wavelength, all the way to the blue, which is a shorter wavelength. Okay, I don't know if you can see this line or not. Does anybody see that there is one in here, which looks like violet? Yes? Yeah, it's faint. That's what the point of it. So the spectrum is there, but you're supposed to see it with your visible eye. We can see anything that is in the red region. This is actually dark red. This is getting into very long wavelength. And from after that, it's going to be infrared. We're not going to be able to see that. And then this one is actually violet. And then after that, we're not going to see ultraviolet. So this is what we see with our own eyes. This is the visible spectrum for helium. So if you see all of these lines, including this, what is it, turquoise? I think it's still green. So this one, then there is a blue in here. There is another blue in here. There are 3 blues in here. One of the, no, actually, turquoise, 2 blues, and so on and so forth. Anyway, this is actually a visible spectrum. This is actually your spectrum. Can I ask you a question? Is this an emission or is this an absorption? What do you guys think? There is nothing, it's not part of the lab anyway, this question. I just want to know. What do you guys suspect? It would be absorption if these lines are actually dark and the whole light is actually green, white. I mean, all of the colors are in there. I mean, probably if this entire region is red, fainting to orange, fainting to yellow, fainting to green, then from green back to blue, and blue starts to change to probably violet. If I see that, that is what is a continuous spectrum. And if I detect that there is a line in here missing, which is black in this case, because it's missing, I can see it. There is another line that is dark in here. There is another light, dark and dark and dark and dark. That is the absorption. So this is actually, and I'm glad that somebody is actually participating. That's actually good. That this is actually an emission. Emission, there are no other lights except this ones. It's emitting. So it was excited helium, and the same thing with neon. Okay? But it doesn't matter. Like I said, the lines are going to be numerically the same, number-wise. Just numbers don't change. Unless the substance is moving super fast. In which case you will have something called the Doppler effect, and that is going to shift the entire spectrum one way or the other. If the helium is moving away from us, in a star that is moving away from us, this entire spectrum, as you're looking at it, will shift one way. Now, if it's coming towards us, this entire spectrum actually will shift towards us. Shift toward the higher frequencies. So just by looking at the spectrum, if the lines are exactly where they're supposed to be, numerically, then I can tell you this helium is not going anywhere. It's staying in its place. Now, if I see this line shifting a little bit, and this one with the same amount, with this one with the same amount, then I can tell you this is moving away from us based on the gap that I'm looking at. The bigger the gap, the faster it's moving. The same thing. If the entire spectrum is moved toward this side, is actually coming towards us. So there are a lot of things we learn from the spectrum, not just the composition, but also the speed of the things that is moving, that is making them, where they sit. And that's how we determine actually that the universe is expanding, just by analyzing the spectral line for certain. Did I say that correctly? Yes, yes. For certain emissions from a special type of novas, we were able to determine that the universe is expanding, actually. They're moving super fast, okay, away from us. At least the faraway galaxies, the close away galaxies like Andromeda, just by doing spectral analysis, actually we saw that it's coming towards us. Andromeda and our own galaxy at some point in the future, they would collide and become one big galaxy. I think they gave it a name already, but what is it? No. What is the galaxy? Milk Dramada or something like that. That's the name for the new galaxy that is going to form about 5 billion years from now. I guarantee you, none of us is going to be there to see it. I need lines. Okay, I need these numbers. We're going to take them, and you're going to fill this column of your table with those. Okay, the dim red, the number starts from the high to the lowest because it's a frequency, it's wavelength, I'm sorry. The wavelengths are given to you. The highest number is 706 down to the 447, okay? And don't change the units, leave them in nanometers. These are given to you in nanometers, which is a typical unit for wavelength, that's a distance. And in here, it's also in nanometers, so you keep the numbers intact. Having said that, let's move on to GeoGebra now. And let me stop sharing that screen with you guys and see if it pops up. Okay. We're going to share screen now. And it's this screen. So when you click on the GeoGebra, you are in the screen, okay? Trying to give you in here a visual of how the apparatus look like. And at this point, okay, I'm sorry. Hold on. There is something missing in here. Okay, so the expression for D, I guess it should be, we're going to be using, what is it, 1,000 lines? So we're not going to be using the 500 lines per millimeter. We're going to be using 1,000. I'm missing some text in here, okay? Oh, I'm sorry. So we are supposed to find what D is. So let's go back into the GeoGebra. I'm sorry. So the first part is actually finding what GeoGebra is. What D is. So I have to change activity. Right now I'm in the hydrogen activity. I need to go back to the helium activity, okay? The helium activity is the one that I need to be in. So make sure that you are in the right place when you're doing that. If you go back to the instructions, let me stop this one quickly and share with you the PDF file. The PDF file, the first part that we're dealing with, we're putting a lamp in here that is helium. Okay? So the distance, so these questions are just for the diffraction and the screen. What we're doing now, we're putting helium. That's why we have all of these frequencies for helium. Okay? For helium, we're going to take L in here, and L is going to be given. So it's a fixed distance. Okay? I'm going to take it to be 50 centimeters. So that's fixed in the lab. Actually, when you come in, you're going to find that distance is fixed between the diffraction grating and actually where the lamp is. So that distance is fixed. If it's not fixed, just measure it yourself, and you're going to find it. For our lab, it's going to be a fixed number. So what we're going to be measuring in the lab, we're going to be measuring x1 and x2, and then of course we'll get x, which is just the difference of the two divided by 2. And then from there, we're going to use this formula in the bottom to find what d is. Okay? So this should give us what d is. So let's go to the activity now. So we're going to measure the diffraction grating. So we don't know what d is. So it might be 1 micrometer or 2 micrometers or whatever this d comes up to be. Okay? And a micrometer is about 1,000 nanometers. This is still big compared to the wavelengths of these things in here. Okay? So, but the wavelengths are about 700 nanometers. So it's still within range. Okay? So it's not that big. So let me go back into the Geogebra activity. So there are two activities in here in this very same pile. One of them is the helium, which is the one that you need to start with. And the next one, after you do the helium, you're going to do the hydrogen. So for right now, we have the helium. And we have specific frequencies from the table. Remember, the table has different wavelengths. This is how much wavelength, this is how much wavelength, this is how much wavelength. So if I do the value of one of them, which is probably what is it, 706.5 or something like that, I'm not sure. Now it gives me x1 and it gives me x2. And x should be computed between the two, the difference of the two divided by 2. Okay? So 77 minus 27 divided by 2 is roughly about 25.5 centimeters. So that's the x, the distance between them. Now it's going to give me d actually. You see? Let me go back. So this activity will give me both x1 and x2 and x and d. So I go back into my table in here. Let me stop sharing this one so that I have you follow me with what we're doing. Now we're going back to this table and actually enter these values for that frequency. So I put 706. I don't know if the 706 is the correct number or not, but I put 706.5. Let me look at the frequency. It's 706.5. So for 706.5, I have L to be 50 centimeters. Geogebra will tell me what L is. I have X2, which is 77 point something. I have X1, which is 27 point something. I have X, which is 25 point something. And I have D, which is in micrometers already, 1.00 something. I need to keep 4 sig figs for this lab. So the next thing that you guys know is going to change the frequency from the wavelength from that of 706 to the next, which is 667.8. So the next number I'm going to put in there is 667.8. So let me stop this screen. Let me go back into the Geogebra. So L is 50 centimeters. I just want to confirm that, okay? L is fixed at 50 centimeters. So the next activity is 776 point, I think, something. I don't know, oh, not 670. I'm not sure, okay? So you're going to put the correct numbers in, 676 point something, okay? So now, you go by the table, okay? Again, you have X1 and X2 and X and D, okay? So you're gonna come back to your activity in here, and you're going to report the data in the table. So the next one, which is actually, I probably put it wrong, which is 667.8. Okay. And then I put 50. This doesn't change for the entire lab. So you can put it 50 centimeters all the way. So don't put 50 centimeters, it's 50 already. Okay, in the lab, L says it's 100 centimeters. Don't ignore the lab, okay? Ignore the instructions. Use the 50. Use what Geogebra is saying. Jasmine? Okay, so make sure you follow what the Geogebra is saying. If it's saying 50, your numbers will be completely off if you use 100 centimeters, okay? So don't do that, okay? So go with what Geogebra is telling you. So it's 50 centimeters, use 50 centimeters, okay? Because basically when we did that in the lab, actually for my astronomy class, what happened was some of the lights, at least the longer wavelengths, they were outside of the ruler. So people were having like a white piece of paper behind it, trying to see the frequencies, and they had to do extension measures and all of that. So we actually had to bring it closer. So I remember that from the astronomy class. That's why I had to change the L in there. Anyway, So we have the L, we have the X2, we have the X1, we have the X, and we have the D. So we have everything in here. GeoGebra is going to be nice enough to give you everything. Make sure you average your D's then at the end of the day. So you don't need to do the math in here. Everything is given for you. So you don't have to pull a calculator and start doing square root and which number I have to put here and there. So everything is given for you. And now that D you need to use for the next activity. So the average D, you need to take it and use it in this activity. So what you do in here, let me go back in the second one, because now this is the hydrogen. Hydrogen, we have D from the previous lab. So whatever D is, it's going to be a single number, okay? So it's going to be the average D, because that's the distance between this lines and the diffraction gradient. And the L is going to be the same number, 50, okay? So now it's going to give you X2 and X1 and X. So let's go back into the activity and see how that works now. Okay, let me go and share with you the GeoGebra. So now we're doing the hydrogen. So we're going to change activity now, okay? So it's going to ask me, give me D. So I'm going to give it D in micrometers, not in meters, okay? So if it's 1, I'm going to use 1. If it turns out your average to be 0.9983, remember, I'm asking for 4 sig figs. That is the number, okay? So that is what you get from the previous activity. So you cannot do the second activity. That's why I was kind of confused a little bit. What D should I use? But I was in the wrong lab anyway. Are you guys seeing this or not? Because somebody made something in the chat and I cannot see the chat session unless I stop sharing. Okay, no. Okay, so let me go back into the activity. So now I have my D from the previous activity, which is the average of the D. So you need to do that. That's something that you have to add all of the quantities and divide them by their number, which is 7 or 9, depending on how many frequencies you have in there. So now this table now gave me both X1 and X2 and what lambda is. Okay, so it gave me both X1 and the different frequencies of what lambda is. So all I have to do now is take X1 and put it for the first light. So the first light, I'm going to take this 3 lines in here. The entire row. So let me go back in here and show you. So the row from the first one, I'm going to take X2 and X1 and X, which is just the difference of the two. I don't think that GeoGebra is going to give you X. All you have to do is just do X2 minus X1. And it's going to give you the wavelength, which you're going to put in here. So that answers this entire thing for the red lights, okay? Let me see if is it the long wavelength or the short wavelength? Let me stop in here to see if this is red or what color are we talking about? Yeah, the longer is the red. The shorter is the blue, okay? Or at least from high to low. So if this is red, this is probably what, green or blue or something like that. I'm sorry, it's yellow or something. It's green, probably different color. So at least you start from red and get into violet, okay? So this is the numbers that I'm getting. So the 666, the higher number, and the X2 and the X1 will all go. Let me go back into the table. The 662 comes in here and can be compared to the 656. And the X2 goes in here and the X1 go in here, and this is just the difference divided by 2. Just take this X2 minus this X1 divided by 2, okay? So that's going to be your X in there. So everything is given to you. Now, the 662, was it 662 minus 665 and divided by this number? That's going to be the error. So let me go quickly to check if it's 662 or what number I got from there. I got 666.29. I'm sorry, 666.29. Remember, I am keeping 4 sig figs, okay? So this is 5 sig figs. So I need to get rid of that extra digit. So what is the GeoGebra? So this is 666.4, I guess. 66.4. So the minus 656. So the answer is 10. point something or 9 point something, 9 divided by 666 or 656, it's going to be a very, very small error. Okay? So as a matter of fact, the error should be about, in this case, the difference divided by the known number, and the known number is the one that is listed in here on this table, the fixed number. Okay? 6, oh, I'm sorry, divided by 656. Oh man. So it turned out the answer to be 1.5% error. Okay? So the error in this case, if I go by, please don't go by the numbers I just ran because your numbers might be different, okay? The error is about 1.5%, okay? So the error should be small, okay? If they're too big, don't blame anybody because you blame it just on the fact that you're getting this data from simulation, not the real measurements. Okay. Now, this is only positive numbers. So if the answer is negative, ignore the sign. Okay? If the answer is negative in here, just ignore the sign. So that's you're going to do and answer question 3 and question 4. And that's it. Don't do this guy. That's all the lab. No, you're not dividing by the experimental value. You're dividing by the known value, which is the theoretical value, the last one, the one that is hard-coded in you. You take the one that GeoGebra gave you, you subtract from it the one that is actually on the table, and you divide by the one on the table, okay? And make sure it's positive number, and you multiply it by 100, by the way. Don't forget to multiply by 100. And that's it, okay? Any questions about this lab? No? Let me check. Okay, we're going to start the second lab, but before I start the second lab, I'm going to take a pause, if you guys don't mind, for about 5 minutes. Please don't go too far, okay? Yes? Jasmine is asking, okay, this lab, the question is basically, is everything clear on this lab, or do I need to explain something else? Jasmine? Okay, on the question of the percentage, let me go back onto the question of the percentage, okay? And you guys have the right to ask the question. So you're going to get something from GeoGebra here. Is this correct? Yes? No? Okay, so now we have a number from GeoGebra on this thing. We're going to subtract from it this one. Just do the difference, that's it. And then divide by this number. Correct? And you multiply it by 100. That is your answer. Except if it's negative, ignore the sign. What you put in here is always positive. Okay? If it's positive, then just ignore the sign. Ignore the sign, end of the story. So if you do the calculator, it might give you negative 1.5%, or it might give you positive 1.5%. In either case, ignore the sign. Just put the number in here without sign, okay? And if you forget to ignore the sign, don't worry, okay? I'm going to ignore it for you, because the errors are always strictly positive. Does this make better sense, hopefully, Jasmine, and everybody else too? Okay, good. So I'm going to take about 5 minutes to go and get my coffee, and I will be back. So please don't go away, and also to give my computer a chance to hopefully build a little better chart so that we can finish the second one. Thank you. Don't go away, okay? I'm going to pause probably the recording also. Yes, the question from Jasmine about part 3, no, you're not, because really we can't do that. We need some materials in there to do that, okay? I mean, you can only mimic some things only in the lab. You can't do everything, okay? Remember, this lab And this next lab are really what you're going to make a decision which one you're going to do as for credit and which one is going to be for your extra credit, okay? So this one is one of them, option 1. You can say, okay, I'm going to do lab 11 and I want it for credit, so you're not going to make any mention whatsoever when you file your report. Or it might be the one that you want it as an extra credit out of 10, basically, not mark it out of 20. And the other one to be actually for credit, okay? So depending on how you want it. I don't want to really make that call for you because you might feel one way or the other. I don't want to be the one who's making that decision for you. Now, so the lab report in here, let me go quickly for the lab report in here because it's important. GeoGebra, when you're doing the hydrogen lines, will give you, of course, you're already going to put a value in here yourself for D that you get from the previous lab. This is from the previous lab, the same value everywhere. L should be also the same value everywhere. It's 50 centimeters, actually. X2 is going to be given by GeoGebra, and X1 is going to be given by GeoGebra. And this value is going to be given by GeoGebra, and you're going to compute this value yourself. You're going to find the difference divided by this number, the difference between these two divided by that number, and it's going to be the value in here. And in here, you need to take this minus that divided by 2, okay? So this, make sure you do it to yourself because it should not be hard to do. And then you're going to answer the rest of the questions, which is typical that we normally do in this class. And based on your data, your observation. Now, part 3, you don't do. This one in here, you don't do it because we didn't cover it and we're not going to be doing that. Whether you're doing this lab as for credit or not for credit, ignore part 3, okay? And same thing, the entire part 3 is ignored all the way to its results, but conclusion for the entire lab is required, okay? So we're done with this lab. Yes, we don't need it anymore. Yes, no? Is there any question for lab 11? Okay, so let's move on now to lab 12. So I'm going to go back into my screen and go to the assignments again and pull lab 12 from it. Let me share with you the screen so that you guys have a feel of what everything is on this activity, because there are a lot of stuff in here that you need to be looking at. From lab 12, of course, you have the actual lab activity itself, which you will need to go through, which we're going to talk about. You have an Excel file called the auto roller, which is a must. You have to have this Excel file to basically mimic what are the chances for a specific atom to go radioactive, okay? To basically emit radiation by itself. And then you have the this Excel file that is going to actually that is required actually for the actual calculations. And then you have this PDF file that is where you're going to actually print it and do some plotting. And finally, this is the report file. So there are a lot of stuff as compared to the previous lab. This is far more involved in terms of at least work involved. So I'm going to open this file. We'll start, of course, with always with the instructions. I'm gonna stop sharing the internet, basically my internet. And let me take the attendance. I don't think I did already. And go to Paint. And paste it. Okay, so this is the attendance for today. We have quite a few people who are not here for some reason. Okay, for those who came in late a little bit today, oh, I'm not sharing that screen. The word is basically you have options between 11 and 12 to be full credit. For extra credit, one of them, and for regular credit is the other. And you're going to tell me which one is for the extra credit. I'm going to assume the other one then is the normal lab. So again, I assume that probably you didn't also cover radioactivity when you did this class, did you, in lecture? No? Okay, sorry. Okay, basically this stuff is happening not on the level of the electrons. This is way inside the nucleus itself. So again, you have the atom which has a nucleus and an electron. Lab 11 deals just with the movement of the electrons in the upper layer. Now, what we're talking about is inside the nucleus itself, inside the actual nucleus of the atom itself. So what's going on in here is that you have sometimes things happen by themselves. Sometimes the entire nucleus is not stable and emits what is called an alpha particle. Basically gets rid of four of its elements at once. 2 protons and 2 neutrons. They will leave within with a certain kinetic energy, and that is called an alpha radiation. Sometimes what happened was inside the nucleus you have a neutron, for example, changing into a proton and emitting an electron in the process. So the atom was this type and changes completely to a different atom. So you had, for example, dealing with an element, and now you are dealing with a completely different element on the periodic table. Because of this change, because now the nucleus has acquired an extra charge. But the electron that has left now has to, is coming up with an extra amount of energy, and this is called a beta-decay. Now, sometimes what happened was actually the proton actually changes to a neutron by basically emitting what is called a positron. So, and that is actually an electron that is positively charged. And the electron that is positively charged is completely highly unstable because it's going to encounter any electron and basically destroy itself. So this type of the radiation is called actually the beta-decay. And then there is another type when the atom is just unstable by itself and emits radiation, just like the electromagnetic radiation we were looking at earlier in the previous lab. Light, basically, but it's extremely high energy. This stuff is happening on the nucleus. So whatever we're talking about in terms of energies are extremely high. And the radiation that is going to come out from this one is gamma rays, super high energy electromagnetic radiation. So this is called the gamma decay. So there are these types, and there are some things that basically can involve different mixtures of different particles that we can talk about. Anyway, what characterizes the nucleus itself are these 3 numbers. The number of protons is Z, the number of neutrons is N, and their sum is the atomic number. So A, N, and Z is what characterizes every single element from the next one. P is what determines if you are dealing with gold or silver, if you're dealing with iron or nickel. It's really the number of protons because that's the same number of electrons in the outer shell. Now, the neutrons, you can have the same elements. Chemically speaking, it's the same compound. It has the same chemical properties, but it has different masses because they have different ends. So you could have the same number of atomic numbers, but different ends or different P's, different Z's. I'm sorry. So that's basically what determines the properties of the nucleus, and hence the entire matter. And we usually use this new representation for every single element in here. Z is in this case the number of protons, and A is the sum of the protons and neutrons. So that's basically how we represent it. So if you see, for example, aluminum 1327, you know that it has 13 protons, namely 13 electrons when it's electrically neutral, and 27 nuclear elements, basically protons and neutrons. So you do the math. 27 minus 13, that means it has 14 neutrons and 13 protons. Okay, that's for this type of aluminum 27. Now, Xenon 131 has 131 elements in the nucleus. 54 of them are protons. So you do the math, you will find that 77 of them are actually neutrons. A lot of neutrons in here. Okay, because you have a lot of protons. Basically, what's going on in here is, for the hydrogen atom, you only have 1 proton. You don't worry about it. For the helium atom, you have 2 protons next to one another, and they're both of them positively charged. So electrically, they should repel one another. But they're very close from one another, that nuclear forces take effect. So they're attracted by nuclear forces. The nuclear forces keeps them together, but their charges will try to repel them apart together. But in this case, actually, they will not stay stable. So what you need in this case, you need neutrons that have no electrical charges, but they actually play the game of nuclear forces. So they will fuse the two protons together with them, and they will keep now the helium stable, the helium nucleus stable. So the neutrons are actually needed to keep the entire atom stable, because the more protons come into play, like 54 of them in here, the more of this instability due to the electrical charge. So you need more and more protons to keep this thing from basically falling apart. What happens in this situation is when you have a lot of protons, the element gets heavier and heavier. The protons that are on one side and the protons that are on the other side, opposite on the nucleus, they're far away apart that their nuclear forces, they don't feel them at all. So the only thing they feel is actually the electrical forces. The electrical forces have they reach wherever the charges are, but the nuclear forces are very short range. So if they're on the same nucleus, the same protons that are sitting on different edges of the nucleus, they're actually going to repel one another. They're going to actually try to start to tear apart the nucleus. So what happened in this case, that's why you need glue in there to keep them together, and that glue is actually the neutral particles, which are neutrons. So neutrons play a very, very important role in keeping elements together. So they are very needed, very much needed. But after a certain time, of course, even those, they were not going to be they were not going to be able to keep the atom from emitting radiation. Sometimes it gets excited and basically splits or something by itself. So in the case of uranium, it gets 2 protons and 238 elements inside the nucleus. That means you have 238 minus 92, which is 146 protons. So that's how we get these numbers. That's how we arrive to these numbers inside the nucleus. So we have some definitions. We call an isotope every 2 elements that have the same chemical properties, but they have different masses. Namely, they have different number of neutrons. So you could have a uranium-238, for example, or uranium-235. Both of them are uranium. Both of them have 92 protons. Both of them have 92 electrons where they are neutral. So electrically, they enter the same chemical reactions. There is no problem with them, but they have different masses. The 235 is 3 neutrons short than the 238. So that's what we call an isotope. An isotone, they will have the same number of neutrons, okay? So having an isobar will have the same sum, basically, regardless of which combination you play with. So that's basically some definitions. The most common word used is isotopes, and the isotopes is usually dealt with in chemistry a lot because you will have different physical properties, whereas the chemical properties are identical, okay? So I mentioned the alpha decay. So uranium, for example, goes into thorium and losing 2 protons in the process, and losing actually 4 elements from altogether, namely 2 protons and 2 neutrons for a total of 4. So it lost 2 protons, and in addition to the 2 protons, you have 2 neutrons, and that has actually the alpha particles, which is no more than just the ionized helium. So helium with no electrons. So that's basically what an alpha particle is, and it's super fast. Of course, if it travels far enough, it's probably going to acquire electrons and become neutral helium. But an alpha particle by itself is an ionized helium nucleus, basically, the nucleus of a helium atom. So that's one way. That's one decay. There is actually the beta decay I was talking about in here, in the case, for example, of carbon changing to nitrogen and emitting an electron, an antineutrino in the process. So this is another elementary particle in here. Don't worry about what it is, but at least just to make things balance out. So in this case, the electrical balance is you have 7 protons, subtract from them 1 electron. 7 minus 1 is 6. So I started with positive 6 charges and end up with positive 6 charges. The number of elementary particles inside did not change. I had 14 in the nucleus. I still have 14 in the nucleus. But one of the neutrons that existed now has been converted to a proton. So a neutron that was in there, so I have 14 minus 6 is 8. I had 8 neutrons to start with. Now out of the 8 neutrons, I'm left with 14 minus 7, which is 7 neutrons. So one of the 8 neutrons has become actually a proton and emitting an electron in the process. So this is the beta decay. The beta positive decay is another reaction that's going to emit an electron that has the same mass as the electron, the same value of charge as the electron, but its sign is actually a positive charge. So in this case, for example, you have the sodium changing to the neon, and then giving you what? A positively charged electron, and with a neutrino this time around. This is an antineutrino, this is a neutrino. Ignore this neutrino's business, okay? For as far as your lab is concerned, they are irrelevant. Anyway, in terms of the charges, I started with 11 positive charges because I had 11 protons in the sodium, but the neon only has 10 protons, but I have a positive charge at left, positive charge plus 10, that's 11, and then here I have 11. In terms of actually the number of particles inside the nucleus, I started with 22, and now I still have 22. But for some reason, I had 11 protons, so I had 11 neutrons. But now I only have 10 protons in this element, so that means I have 22 minus 10, which is 12 neutrons. So the number of neutrons has incremented by 1 in this reaction. So in other words, 1 proton changed to a neutron. So that can happen too. A gamma ray, for example, if you have an electron and an anti-electron, so here is your electron, here is your anti-electron, they meet together and they cancel one another. They annihilate one another, and now all of a sudden you have a gamma radiation, very high energy. You lost matter completely. Pop, there is nothing. Electron, now you have nothing, but you have radiation, you have energy that comes out of it, which is a highly energetic energy in here. Okay. Now, for this can happen this way, or it can actually, for example, for what is deploying lead? Yeah, for lead, for example, and stable lead, nothing has changed in terms of the protons or the neutrons or nothing. The only thing that changed, the entire atom was sitting basically with high energy. I mean, the nucleus with high energy, and now it has lost some of its energy in the form of gamma radiation. Okay. So that's basically what you're supposed to do in here. Now, I'm going to do this first two examples, and hopefully you guys can do the rest in here. There is this table in here, this link. So you're going to look at, what is this? Radon. And then see, it's going to give me an alpha particle. So from 86, I need to subtract 2. So I need to go to 84, an element who has the chemical properties of an 84. So let's look for it in here. So I started with an 86. Here is an 86. Okay. And if I hover over it, look at here, look at this area. Oh, I'm sorry. I'm not showing probably the screen in here. I need to share with you my screen in here. So when you click on the link, you'll come to this page in here. Okay. So every single element in here, zinc, for example, I'm looking at zinc in here. Look at this area in here. It gives you all the properties of zinc that you're hovering over. So if I go to cadmium, in here, I have the physical properties of cadmium. Here is radon. It's an 86. So this is nice. It's organized with the increasing numbers. So if I'm looking for an element, here is an 86. I said out of the 86, I'm going to get an alpha particle. Out of alpha particles, that means I have 2 protons that have left. That means I drop by 2 in the Z number. So I'm going to go into polonium now. So if I go from 86, I'm going down by a factor of 2. So 84. So it's going to be PO. So I go back into my activity in here. And put PO here, and with the next number to it is 84, because 86 minus 82 is 84. And in here, I'm going to put, what is it? 211 minus 4. 211 minus 4 is 207. So this is one way of writing polonium, okay, in this format. I'm going to stop sharing. No, actually, let me see. Yeah, I'm going to stop sharing this screen in here and share with you the lab report form, because this question you're going to ask, I'm sure. So I'm going to go back into the lab report form and try to answer this question for you guys. And how to do this writing in here. Let me get into the section for the nuclear reactions. Okay, so let me go back into Zoom. I'm going to share with you the lab report form. So I'm in this section now. I know the answer is polonium, but I know the number went from 86 to 82. So the answer in here is going to be 84, and then polonium, and then next to it 207, which is 211 minus 4, which is 207. So this is the isotope that I'm going to write in here. Actually, I probably wrote two. It's going to be capital P, O, lowercase o. Always the elements start with the, like in here, for example, helium, lithium, gold, and this is only one letter. So when you have two letters, you always, the first letter is capital, the second letter is lowercase. And then what I'm going to write the first one in here is, because you're going to ask me, how am I going to write this one with the one in the bottom, one in the top? Don't worry about it. Just write it to the left and the right, okay? The left is being the value that is for the Z, and the right is your value, which is the sum of the two. So this is actually an isotope of polonium. So let me go back in here and show you. Where is my... Okay. Sorry, I need to move things because right now I'm not seeing this whole screen in here. Not that. Here. Okay, do you guys see the same screen I'm looking at now, which is the periodic table? Yes or no? If you type something, I can't read it right now because I'm in this mode, so I really need to hear it now.
Yes.
Yes.
Okay, very good. Thank you. Okay, so if I go back to the polonium now, the one I found, look at the common properties of the polonium. Look at the number in between in there, okay? So if I go with the mouse, it's going to really, where is my pen in here? Here's my pen, let's see here. I don't know if you can see this one in here, this number, the one I'm looking at in here, namely the 209, the atomic weight. So it's not 207, whereas I11 minus 4 is 207. So this is not the most common isotope of this element, but just it's an isotope. They have the same number, which is 84 as far as the atomic number is concerned, as far as the number of protons is concerned, but the atomic number is different. It's not the most common one, which is 209, which has 2 extra neutrons than this one, and this one is 5. So the answer is, the way I showed you, you're at 84 PO 211. Let me do the second one, because I promised I'd at least I do another one with you guys. If I can ever find it. The second one is an element giving you lithium 13. So let me stop it in here. Let me go to that. So in here, I have an electron. So I have 3 minus 1. That's going to be what? Positive 2. So I have a 2 in here. Okay? So I need an element that has 2. But in here, the number of 8 does not change. So it's 2 and 8. So this is a highly, highly unstable atom in here. So in this case, one of the protons that was on the top need to convert them. I mean, one of the neutrons that was on the top need to convert and stay in here. So because this is a beta decay, the A number doesn't change. So 8 doesn't change. It's this number that has changed from whatever value to 3. 3 minus 1, it has to be 2. So if I go back into this periodic table in here again, the one I was in, sharing this screen, and I'm going to share this screen with you guys. So here is where the lithium is, 3. And I have to go back now to where I started from, which is 2. So in this case, 2 yields 3. And 2 is helium, actually. But helium, as you can clearly see from its properties, it's 4 in here. But I have helium 8. This is a highly unstable helium. But it's an isotope, according to this data. So the answer, again, I'm going to go back into the lab report form. I'm going to come in here and write the answer as being, first of all, I know it's going to be helium, and I know that I started with 2 protons on it, so it's He, but I had 8 protons and neutrons inside their nucleus. So that's the answer, okay? And I hope you guys can finish the other 2 in here, just by going through the periodic table and trying to navigate your way through this. Okay? Here, for example, I have a 9, and I have a 1. So this number must be 9 minus 1. So this is 8, actually. So I need to find what element has 8 protons in it. It should be next to fluorine. I have gold in here. It's going to decay into something, but this is an unstable atom. So it's probably this one. So there is a gamma decay in here. So probably this whole thing doesn't change. It's going to be similar to this nuclear reaction. Okay? So that's basically, in a nutshell, how this thing works. Okay? Any questions so far? Because what comes next is a little bit more involved. So basically, a given atom itself, in order for it to go to decay, is not really something that is for sure. But on a greater level, when you have a lot of number of atoms, even on a small sample, there is a rhythm with which they go, and that's basically what we're trying to simulate in the next activity. Okay, and here it gives you the different kinds of decays and what causes them. Is it the strong force, nuclear force, basically, or is it the weak force, which is the nuclear weak force, or is it the radiation, like for example the gamma decays? So this is just classifications, and so you can look in here. The beta decays, both beta decay, positive and negative, or the capture of the electron, actually, which is another process also. So every time there is an electron involved or a positron involved, is actually the weak nuclear force. Every time there is an alpha particle in here, or in this case a single hydrogen, or in this case a neutron, or any time there is a change in the actual protons numbers or neutrons numbers, then in this case actually it's the nuclear forces, the ones that are responsible for that. In other words, you have a proton going into a neutron, or vice versa. That's why you have strong nuclear forces causing that stuff. And in here, you have an atom that is unstable and basically emit light, and that's an electromagnetic radiation, electromagnetic force, EM forces. Okay? This is no different, honestly, than the first lab, which was the absorption and emission, except this is an emission spectrum in this case. Okay? So now the half-life. The half-life is what I was talking about in terms of being a probabilistic effect, and that's why we need that autoroller to conduct the activity. So first of all, a half-life is the time it takes for half the sample to leave, to go away, to convert to a new element. So for example, sodium 22 is unstable with 2.6 years. Every 2.6 years, whatever you start with 1 kilogram, after 2.5 years or 2.6 years, you're going to lose that half kilogram. You end up with half kilogram, which is basically 500 grams. After another 2.6 years, that 500 grams will reduce to 250 grams. After 2.6 years, you're going to reduce that number from 250 kilograms to 125 kilograms. So basically, every 2 years, you're going to lose. Every half-life, you're going to lose half the amount that you start with. So that's basically how the law works. Are you going to ever run out of element? I mean, you're going to be down to a few atoms, but technically, it should not. Mathematically, at least, it should not. But practically, yes, it does. Which begs the question is, what happened to the life of the elements that are very, very short life-lived? Why do we see them? Because if the Earth existed for billions of years, why do these things exist? And because the entire process is actually cascading. There are some that takes billions of years, actually longer than the universe, to lose half of their life, half of their amount. Half-life is much longer than the life of the universe. And some of them that are actually within minutes or seconds. So you have to, so it starts from one to the next, to the next, to the next. So the process actually is not just one transition. It could involve several stages, okay? So that's basically a chart in here giving you for which element? For the sodium. and giving you exactly what I was talking about. So you'll always have a fraction of sodium left, 22. Okay. So so the half-life of iodine 125 is 60.1 days. How many days must we wait for half of the sample to decay? It's obvious in here, 60.1. Because if you have the sample and you wait 60.1 days, you're going to lose half of the sample. This question has a part 2 to it, though. 3/4 of the sample to decay. Okay, we started with the sample. We lost half of it in 60.1 days, and we're going to lose half of the half in another 60.1 days. So after 120.2 days, we're going to lose 3/4 basically of the entire sample, the one we started with. So for the 15/16th of the sample to decay, how long does it take? So you're going to do basically the analogy and try to guess the answer to this one. So this will be 15/16th of the sample to decay, not you wait until this is the last 15/16th. So basically, it's going to be a short fraction of this number of days, okay? So now if the activity is okay, if the activity of a sample of hydrogen-3 decreases to 1/8 of its original activity in 37 years. So after 37 years, you lost 1/8. Okay, you didn't lose 1/2, you lost 1/8. So how long before you lose the whole half of how many half-lives passed? So again, the 1/8 is not the 1/2, so you divide 1/8 by 1/2, and you should find a number in here. Okay. So again, I was talking about the probabilistic effects, and this is how the graphs would look like. So let me get into the activity. So let me explain what this activity says in here. You have an atom. You have basically that is represented by the number of dice in here. Okay. And how many times you roll them? Each time a die will come with facing value of 1, you eliminate it and say that decayed. I don't need it. You guys understand the process? So you have, for example, 100 dice in here, the 100 die in here, and you throw them at random. We have actually this activity in the lab. We have this many actually. You throw them at random, and you look at them and see each one of them is 1 with the face 1 on top. You say, okay, this has decayed, so I'm going to go and put it on the other pot. So I don't need them anymore. So now you have the certain number that is left. Let's say, for example, out of 100, you lose 10. Now you're left only with 90. So you come in here and you say, I removed 10 and I'm down with 90. Okay. And then you throw the 90 again. And then when you do the 90, it's going to tell you, okay, now let's say, for example, you lost 5 because 5 came up with face up showing 1. And the other 85 are still came up with any value other than 1. Okay, so you're going to put 5 in here and 85, and you continue this process until you do it for 20 times. After 20 times, you stop. Okay, you guys understand what the idea is, at least conceptually. Now we're going to get into an Excel file to see how that works. Yes? Okay, again, we're trying to say, okay, instead of having a sample decaying, we have actually dice. Okay, we have 100 of them. And what we're going to do in here is we're going to sample as if they're atoms, and some of them randomly chose to go radioactive. Okay, and change, okay, to a different element, whatever that is. They have emitted something, okay, alpha particle, beta particle, gamma energy, whatever it is, they are now have basically checked in as far as the radioactivity is concerned. We take those and get them out of the pile. And then we repeat the process again with the remaining, the ones that did not do the go radioactive. And then again, a certain number of them are going to go radioactive, take those out of the pile, and then keep on doing this at least for 20 times. So we're trying to simulate the radioactivity using this thing. Hopefully, Beth, this answers your question a little bit better. Yes. Okay, so let's get into the Excel probably file. Maybe it's going to explain it. Before I do that, let me open the Excel file first. I don't have it open. So let me go to the file. And this is the auto roller Excel file. Okay, so I'm going to click on it. How much charge I have left on this computer? 76%. Okay, I think it's going to be okay. Before I do that, you need the number of faces on the die. Okay, so let me go into the question. How many faces? Because this is a special one. This is not like the one that you have in the casino. Okay. The instructions will tell you how many to start with. Okay. The instructions tell you to start with 4, do 6, do 8, do 10, 12. And then 20 sites, okay? So we're gonna do, I'm looking at the instructions trying to find exactly which one we're starting with. I think we start with 4 or 6, I think it's 6. No, the types of dice is included, so all 6. So let's do the table 2 in here. I want to see what it is. Okay, use 6, okay? Use 6, okay? So let me go into the Zoom first and share with you the Excel file if I can see it in here. Share Excel file. Okay, so the sides I'm going to put 6 in here, okay? And look what this tells me. 6, the first run, I lost 14. So if I lost 14, I'm left with 86. Say, go back to the table in here. Let me stop sharing the screen in here. Let me go back into the PDF file. And the first run, so 100, I put 14 in here, and I have 86 left in here. So that's done. That's at least the first step. Let me go back and continue now. So we're going to go back into share the Excel spreadsheet. So now our starting point is not 100 anymore. It's 86. It's the last number. So it's going to be 86. Now I lost 16. 16 ended up with 1. Actually, they are here, if you see them. All of these ones there with 1. And I'm left with 70. So I go back into the table now. So remember, I started with 100. I put 14 in here. And now I am left with 86. Now I'm going to put 16 because I lost 16 in the second stage. And now I have 70 left. So I'm going to have 70 as my starting point for the next activity. So I'm going to stop sharing that. And I hope that you guys see the process now, by now. I'm going to come in here and put 70 instead. 70. Now I lost 16 again. 16 of them went radioactive. I'm left with 54. So I go back into my Excel spreadsheet and do the same thing. I mean, my PDF file, my activity sheet, and fill out this form. So now I'm going to start with 54. I lost 7 in this time. And I'm left with 47. And each time I lose one of them, they go radioactive. They disappear from this panel in here. So the next activity is going to be 47. I'm left with 38 now. And here they are. But 9 went radioactive. So 38 is my starting point. I'm left with 31, but 7 of them were active. So I'm left with 31. The next one is 31. And I do this 20 times. Okay? So now I'm left with 26. Okay? 5 of them went radioactive. And 26 is my starting point. 3 of them went radioactive. Now I'm left with, you will notice that as you go along in the process, initially you're going to have a lot of them because you had a lot of sample to start with. But as you go in the process, you're going to have less and less going radioactive. Okay? 23 now. 17. Of course, I'm not doing this step, but I'm assuming that you know what you're doing each time. You're going back to this to the table and filling in the numbers in there. So I'm gonna go. So 17. So I have 11 left now. Another 6 went radioactive, and after 11, I have 2 only went radioactive. So I'm left with 9, and after that, I'm left with 7. 2 went radioactive. And now I'm left with 6 because only 1 of them went radioactive, and here it is. And 6, I'm left with 4. And 4, I'm left with 3. I don't know, I probably exceeded to 20. Now 3 did not change. That's what I was trying to get to. At some point in the process, you might do an iteration and you will have 0. So leave it 0. Don't worry. If it's within a 20, don't worry about that. Leave it 0. Okay. Don't say, oh, I didn't get any radioactive reaction right now, so I'm going to go and do the next one. Don't do that. Okay. So let's say, for example, this is the 17th or the 18th. I don't remember exactly. I think we lost track of this a long time ago. So at some point, we're left with 3 here. 3. And now we're going to say, how many did they go radioactive? 0. So the number that goes for the 18th iteration is going to be 3. 3 minus 0 is 3. So that's really the point I was trying to get to by going as far as I can go in here. So let me continue with this thing. So the next one is going to be 3. So those are 2 different events, okay? Do not ignore the 0. Do not assume, oh, I got 0, so probably it's not going to count. It counts, okay? So I'm going to do a 3 again. So 3 again gave me 0. So that's another 0. 3 again. Now it changed. So I did it twice. So the 17 was 3. The 18 was 3. The 19 probably was 2. You guys understand that? I'm not saying exactly 17, 18. It may have already exceeded the 20. But what I'm trying to argue with you guys is that you have to pay attention to what's going on in here. Then 2. Then 2 again. Then 2 again. Then 2 again. At this point, it seems like it's not radioactive anymore. Look at the bottom in here to see that actually there is some tosses of this thing. So the dice are changing. I'm sorry. Now they changed again. Now 1 of them went radioactive. 1 of them gave me a 1. So now I'm down to 1. And that 1 went radioactive. Now I'm down to nothing. Everything is gone. You guys understand? If I do 0 now, that's it. I'm done. I hope this Excel file explained it a little bit better. Beth and everybody else? Okay, so let's continue with the lab report now, since this is important. So we're going to do now, for our sample, we're going to fill out the entire 2 columns in the same time as we're going, okay? Up to 20. At 20, we don't report anything after that. That's it. At least this part, okay? So we're done with this this entire column up to here, and this entire up to here. That's 10. And then we're 11 up to 20, and we're done with this one in here. And I think that's question number, which question is this? I lost track of the questions now. Yeah, I think it's question number 5. Okay. Since this lab is statistical experiment, one can make predictions regarding the number of dice expected at the 20th roll, as seen in the table. Now, what this table is telling you is the following, that if you start with 4, okay, when you get in the 20th, you're going to get a value between negative 0. Basically, you're going to get 0. Okay. In other words, this process, you will run out of materials, and they will all go radioactive if you start with 4 sides. You're going to check that. You're going to start with 4 and go all the way to 20. Did you get a number that is basically 0? If it is, then you're going to have a check mark in here. If it did not, you're going to leave it unchecked in here. Okay? Same thing in here. If you start with 6 faces, by the 20th, you're going to get an answer between 1 and 4. Either when is there with one dice left, or 2, or 3, or 4. And if you end up with more than that, like 5 or 6 or 7, you're going to leave this one unchecked. But if you are in this range, you leave it as is. Again, you cannot go wrong on this activity. Okay? You're going to tell me what you got in here, and that's it. So whether it checks or not doesn't mean that you're right or wrong. Absolutely. You're going to get full credit for doing it. Because this is a simulation, yeah, it's out of your control, really. So let me go back into the Geogebra. I mean, not Geogebra, I'm sorry, for the Excel file. So at some point, let's do the 4 only, okay? So the 4 faces and the 100. Okay, am I sharing the Excel file with you guys? Yes or no? Because I can't see the chat session. Tell me yes or no. At least one person, please.
Yes.
Okay, very good. So right now, we're starting with 4, and we said it's 100. We ran it once, and that's 1. Okay, so we need to do it for 20, okay? 2. 3. 4. 5. 6. 7. 8. 9. 10. 11. 12. 13. 14. Remember, I got a 0 in here, so I leave it as is. This is 15. 16. 17. 18. 19. 20. So it does not check for me because I'm supposed to get a value of 0 basically. I got a 2 in this case. So my answer will be that's my answer. You might run it and it's gonna, because this is a random event, remember. Lab reports will be completely different, okay? At least the numbers in between. But more or less the statistics should be respected. So I got a 2 here. And I will leave the lab unchecked. Let me go back into the lab report form so that you see exactly how this looks like. What is it? This one. So we are doing now this question. We're doing here. So we're going to put a 2 here. And I don't check this one. Let's say, for example, in here I do, and I find 3, okay? So in this case, I'm going to check this value, okay? So that's it. So some of them might end up checked, and some of them might end up not checked, okay? So let's go back into the instructions. So again, you're going to do 20 for each and every one of those dice, okay? Here is another question, okay? When can you get 0? When can you run out of materials? Okay. Let me go back to the Excel spreadsheet. I think this was 20. Okay. So I need to continue to get 0 at the end of the day here. So I'm going to do 2 again. I'm going to do, this is 21. This is 22. 23. For some reason, it's not changing. Is there something wrong with my 23? 24. I guess there is something wrong in here, okay? Let me put in here 4. Okay, for some reason, I think there were some issues in there. I think the answer probably could have been different if I probably did not do something wrong in there. Anyway, this is 25, probably 26. I'm run out of it, okay? So if I didn't do a mistake, and I think I did a mistake on this one, probably the first answer probably would have been a check, and this one probably would have actually fallen in the correct place, okay? So let me stop this one in here. And because I noticed that it did not change until I went back to the actual first column, which I think I did earlier, and I think it got stuck in there. It was not running the simulation. So make sure actually your Excel file is running correctly. So basically what it's telling you, it's telling me that you are out of dice or out of materials anywhere between 3.5 and 23. Okay. So maybe 14, maybe 15, maybe 16, all the way to 23 trials, then you will have 0 experiment. Again, you're going to have an agree or disagree in here. Okay. And the same thing for this one. And I think probably I made a mistake on this one in here. I probably will change this lab report form if my computer doesn't die completely on me to have your check marks. Otherwise, it's just this one's in here. Okay. I know this lab is long, and I know some of you probably are wondering when are we going to finish this. I'm trying to finish the instructions as much as I can so that you have an understanding of this. Okay. Now, in order to find the last activity based on this Excel spreadsheet is the following. Again, you're going to start with 4, okay? And you're going to ask yourself, I have 100. When can I lose half of my sample? So again, by counting, the minute you drop around 50, you say, oh, I lost it around this number. So in here, it's telling you anywhere between 2 and almost 3, you're going to lose 50 of your sample if you start with 4. So let's start with 4 again. I'm going to stop sharing that, and I go to the Excel file. So I'm going to have 4 in here. I have 100, the number of dice. So the first run, I lose 77. Okay, I'm down to 77. So I still have more than half. Okay. The second one, I'm down to 57, which is about half. Okay. The third run, 57, I'm down to 39. You see, it's anywhere between 2 and 3. So it checks. I lose half the sample. Let's try it for 6, for example. 6, and I start with 100. After the first run, I'm down to 88. After the second one, I'm 75, more than half still. Okay. After the third one, I'm 61, slightly more than half. Okay. After the fourth one, oops. Oh man, I have to repeat this. I'm sorry. It's my mistake. Okay. So this is the first. This is the second. This is the third. And the fourth one, the third is 54. It's just about half, okay? And then 54. It's below. So anywhere between 3 and 4, according to this simulation. And let's look at the table, what it says in here. Anywhere between 3 and 4 is the correct answer. And that's exactly what we got also here. So there is a check in here. So it agrees. Okay? Yes? So this is actually in a nutshell what your lab is. I think I missed something in here probably. You're supposed to graph this data in here. I probably, yeah, you're going to take this data from this Excel spreadsheet and use it on the second Excel spreadsheet. Let me open it first. Okay, so let me go back into the, that's part of the instructions. Actually, if you look at it, you will find it there. So I'm going to share with you this Excel spreadsheet. So the data, I think for 5 is the one that you're going to use for your plot in there, okay? So you're going to use 5 sites, and you're going to have the numbers that started with, and you're going to put the number that you end up with. So let me tell you exactly how that looks like. Let me stop sharing this Excel spreadsheet, and let me go back into this one. So we're going to start with 5, and we have 100, and the first answer is 85. So I go back, stop sharing this spreadsheet, and let me go back into the first one. So this is actually 85. Okay, what is it? Number removed. What is this numbers in here? I need to read the instructions carefully, guys. Okay. Oh, number removed. I'm sorry. No, not remaining. I can't have. So 15 is the one removed. I'm sorry. Okay. And the second trial is how many removed. So what you're putting in here is the removed, not the actual what is remaining. So I'm gonna stop sharing the second Excel and go back into the first one. I'm gonna put 80. What is it? 20, not. Okay, so probably I did it wrong. Okay, so it's 20 in there, not. So now it's 80. So it's 65. 15 are gone. So the first one was 20, not 15, and the second one is actually 15. So I'm going to go back into the Excel spreadsheet, share with you first one. So this is 20, and this is 15, and continue down. Okay. Once you're done with this one, you're going to get some nice plots in here. This graph, which I needed as part of your report, okay? And this is the log graph, which you will get it too. Ignore this analysis. If you're interested in the math behind it, this is basically what's going on. But at least I need these 2 graphs with your report, okay? You guys understand this lab? At least what to do with it. I know the theory you didn't do it in class, so it's probably a little hard to understand what's going on in terms of the physics behind it. Okay. Please try to do both of them. I think there is a lot of value in doing, actually. I think you'll learn more that way, regardless if it's for credit or no credit. I'd suggest you go through the instructions and try to understand. Which one? Desiree, do you really mean to have this discussion? I'm in private because you're asking me about the video. The video, hopefully, I'm hoping to have it. Look, I can't promise anything. This computer is crashing. This computer, actually, I got a new one. I'm trying to get it up and going, hopefully by tomorrow. And so the video probably is going to go up maybe tomorrow, okay? Hopefully, okay? So if everything works the way that I'm hoping to do, okay? If not, ask questions and make sure you have everything answered for you. And there will be no session next week. This is it. Okay?
Thank you, Professor.
No problem. Okay, I'll see you guys. I guess and I won't see you again, but good luck in your class. I'm hoping to have your grades up after this lab, maybe next week. All of your grades updated. And if you have any questions about your grade, ask your lecturer instructor. Hopefully, she will give you all of the details of the rest of the stuff. Okay? Kareem, thank you very much, and thank everybody. And it was my pleasure having met you in class. And I will do my best so that you're going at least to get your labs done and learn from this class.
Thank you.
No problem. Okay.
Have a good night.
You too. Bye-bye. Thank you, everybody.